So in this video, we're going to be looking at Newton's second law. Now, Newton's second law does have some limitations, but it is very useful in dealing with problems involving friction. So Newton's second law is basically force is equal to mass times acceleration, where the net force on an object will cause the mass of the object to accelerate at a certain amount. So Newton basically implied that the acceleration depends on two things. It depends on force and mass. So in other words, the bigger the force, the bigger the acceleration. The smaller the mass, the bigger the acceleration. And that kind of makes sense here. When I am trying to move, let's say, a truck compared to a little bicycle, I have to apply a lot of force to accelerate that truck to move. Whereas the bicycle, I do not need as much force. Now, if I'm to move something across, the more force I apply to it, the more it will accelerate. Let's take the physics, for example, of ejecting from an airplane. If we eject from an airplane, this is a violent sequence of events that places the human body under extreme amounts of force. Remember, force on a mass creates acceleration. The primary factors involved in an aircraft ejection are the force and acceleration of the crew member, according to Martin Harker, a former physics teacher. To determine the force extended on the person being ejected, we have to look at Newton's second law of motion, which states that the acceleration of an object depends on the force acting upon it and the mass of the object. So regarding a crew member ejecting from a plane, mass is equal to his or her body mass plus the mass of the seat. A is equal to the acceleration created by the catapult and the underseat rocket. Newton's second law is represented by force is equal to mass times acceleration. So let's take a look at what happens now in this situation of being ejected from a jet engine if we change certain variables. If I end up decreasing my force, my mass remains the same, but that means my acceleration isn't going to be maybe strong enough. And what might end up happening then is I can't break through the windshield of the cockpit. If I increase my force too much, that could be too much force on our mass and cause some problems to our pilot. The other problem is now, what if we have too much mass? If I increase my mass and my force remains the same, something now happens as well. We may not have enough acceleration again to break through my glass shield. So all of these variables come into play and they become very important when we're doing certain problems. So I have a question here. Using Newton's second law, how much force must the football player exert to accelerate a 180 kilogram player at a rate of 2 meters per second? Well, we know, based on Newton's second law, force is equal to mass times acceleration. My mass is 180 kilograms, my acceleration is 2 meters per second. When I multiply those together, I am going to end up getting 360 newtons. So let's look at an example here dealing with the ratios of Newton's second law. Here it says what happens to the acceleration of an object if A, the mass and net force decrease by a factor of 4. B, the mass and net force increase by a factor of 4. C, the mass increases by a factor of 4 and the net force decreases by a factor of 4. D, the mass decreases by a factor of 4 and the net force is 0. So to look at these kind of more proportions, we're going to have to set this up. We know that mass times acceleration is equal to my force. So in other words, if we say the mass is 1 and the acceleration is 1, given an arbitrary unit of 1, we know my force is equal to 1. If we rearrange that formula, we know that acceleration is equal to force divided by mass. So in other words, we could say 1 divided by 1. Now we're going to multiply that 1 by these ratios. So in my first example here, we say the mass and the net force decrease by a factor of 4. So that means we have 1/4 of 1 for my force, and we're going to divide that by 1/4 of 1 for my mass. And that ends up giving me 1. So in this case, my acceleration will not change. So now let's look at situation B. Once again, we know acceleration is equal to force divided by mass. In this case, we are going to multiply my force by a factor of 4, and we're going to multiply my mass by a factor of 4. So we end up getting my acceleration, which is normally 1, is equal to 4 divided by 4. In this case, my acceleration is going to be 1. So my acceleration will not change. So let's look at part C. Once again, we're going to set it up. We know area is equal to force divided by mass. In this case, my mass is increased by a factor of 4. So I'm going to multiply my mass by 4. And we know my force is decreased by a factor of 4. So I'm going to multiply my force by 1 over 4. Altogether, I get 1 over 4 divided by 4, which gives me an acceleration which is going to be 1/16 the strength of my initial acceleration. So now let's look at D. In this case, we still set it up, so area is equal to force divided by mass. But in this case, we know my force is equal to 0. My mass is increased by a factor of 4, but 0 divided by anything is 0. So in this case here, there's going to be no acceleration. In our second example, we have a lacrosse player that exerts an average net horizontal force of 2.8 newtons to the right of a 0.14 kilogram ball while running with it in his stick. You want to now calculate the average horizontal acceleration of the ball. So in this case, he's moving with the ball, but since we're assuming he's in constant motion, that's not an acceleration, so that does not apply to Newton's second law. The only thing that applies here is the horizontal force moving to the right with the stick on the ball. So once again, we're going to go force is equal to mass times acceleration. We're going to rearrange this formula to get my acceleration is equal to force divided by mass. In this case, I have 2.8 newtons divided by 0.14 kilograms, which ends up giving us an acceleration of 20 meters per second squared to the right. So for our last example, we have two athletes in a team. We have athlete A and B are paddling their canoe. Athlete A has a mass of 70 kilograms and athlete B has a mass of 75 kilograms. And the canoe itself has a mass of 20 kilograms. If athlete A exerts a force of 400 newtons right and athlete B exerts a force of 425 newtons right, and there is a resistance of, because of water friction, of 380 newtons, calculate the average acceleration of the canoe. So first thing I'm going to do here is draw a free body diagram to help me out here. So I have my normal force going up, my force of gravity going down, I have my force of friction going to the left, and I have force applied A going to the right and force applied B going to the right. So now let's set this up. Our Y forces seem to balance, but our X forces don't. In this case, I have my net force in the X is going to be equal to my force of paddler A applied plus my force of paddler B applied minus my force of friction. We know my net force is equal to mass times acceleration. So we have mass times acceleration is equal to the force of A plus the force of paddler B minus the force of friction. My total mass is going to be 165 kilograms because we must add both the canoe and the two paddlers. And we multiply that by my acceleration is going to give me 400 newtons of force A plus 425 newtons of the force applied by paddler B minus 380 newtons. This is going to give me 165A is equal to 445. Then I'm going to divide both of these by 165 to end up getting an acceleration equal to 2.7 meters per second squared right.